Very often in modern physics, it's postulated that our Big Bang, 13.8 billion years ago, was not the absolute beginning of time and physical reality, but only the beginning of our particular expansive phase or cycle. And this conclusion is based on the idea or the theory that our universe has been expanding and contracting for an infinite amount of time. This model of physical reality is known as the oscillating or bouncing universe model. And such a model can be refuted, at least in regards to the universe bouncing for an infinite amount of time, by appealing to the 2003 Bordoville-Lincoln-Guth space-time geometry proof. Because the oscillating universe model has an average expansion rate greater than 0, the BVG proof applies, and thus it must have a beginning. But what about the law of entropy? Could one appeal to the law of entropy in order to argue against an eternal oscillating universe? Well, as Father Robert Spitzer and many others think, the answer is yes. And one way that they substantiate their claim is by appealing to the odds against our universe having the low entropy that it had at the Big Bang. In 1989, Roger Penrose, a world-renowned physicist from Oxford University, calculated such odds. And the odds that he calculated came to be 10 raised to the 10 raised to the 123 to 1 against. That's a double exponent. In single exponential form, that's a 10, and then in the exponent, you have a 1 with 123 zeros behind it. That's a huge number. And many say that if we were to type that number out without the exponent, and every zero was with 10-point type font, our galaxy would have a hard time holding that number. Such odds against our universe having the low entropy that it had, as Father Robert Spitzer likes to say, is analogous to a monkey typing out the whole corpus of Shakespeare's writings in 2 weeks by randomly typing on the keys of a typewriter. Father Spitzer also likes to use the example of imagining a black sheet extending across the galaxy with 10 raised to the 10 raised to the 123 tiny holes, and one of those holes has a red circle around it. And we're going to throw a pin needle from a galaxy away and hit that tiny hole with the red circle around it. Needless to say, the odds against this happening are very, very, very high. This is akin to the odds against our universe having the low level of entropy that it had at the Big Bang by pure chance. Now, physicists tell us that if the universe has been bouncing, contracting, expanding, and expanding, well then we know that the level of entropy would increase with each collapse of the universe. Jacob Bekenstein, a theoretical physicist, indicates that it would be by a factor of 10 raised to the 80. So if this is the case, well then it follows that the entropy level in the previous cycle to ours would have to have been lower than ours at our initial bounce, at our Big Bang. Well, if the level of entropy would have to have been lower in the previous bounce to ours, well then it follows that the odds for that level of entropy would have to have been even more improbable than the odds for our level of entropy at our Big Bang. In other words, it would have to be higher than 10 raised to the 10 raised to the 123 to 1 against. So if the odds against the levels of entropy in previous bounces would be higher and higher and higher as we go back in time, well then the problem of fine-tuning for the initial condition of entropy would be far more problematic. And if time extends back infinitely into the past, we're looking at infinite improbability. And because it's unreasonable to accept infinite improbability, it seems unlikely and unreasonable that the universe could have been bouncing for an infinite amount of time. So the odds against our universe having the low level entropy that it had at the Big Bang serves as the first piece of evidence from entropy that one can look to in order to argue against an eternal bouncing universe. The second piece of evidence from entropy is found in Richard Tolman's proof. Richard Tolman was an American mathematical physicist who died in 1948. And he noticed that if the universe has been bouncing, contracting, and expanding, then the amount of cosmic microwave background radiation, which is the thermal radiation left over from the Big Bang, would accumulate and increase with each cycle, due to the second law of thermodynamics, which describes how ordered energy progressively moves to disorder. So the ordered energy in the universe would move to disorder becomes CMB radiation at the end of that cycle. Now, Tolman further noticed that the accumulation of the CMB radiation would increase the duration and the volume of each of the cycles. So if the time from our Big Bang to the present is indeed 13.8 billion years, well then, according to Tolman, the previous cycle to ours would have to have been smaller in its duration as well as in its volume. From this, it follows that if we trace the history of the cycles of our universe back into the past, we would discover that the cycles were smaller and smaller and smaller and smaller. And at some point, a finite time ago, we would eventually reach a cycle that was zero in value in regard to its duration and time. In other words, we would come to a boundary of past time. We could not trace the history of the cycles any further back into the past. And if a boundary to the past time, well then a beginning. And if a beginning, well then that militates against an eternal oscillating universe. And finally, the third way that one can appeal to entropy in order to argue against an eternal oscillating universe is by comparing the current starlight to the amount of cosmic microwave background radiation. It's known among physicists that if the universe has been bouncing, well then the starlight of a particular cycle would fold into the CMB radiation as the universe collapses and that cycle comes to an end, thus increasing the amount of CMB radiation which transfers over to the new expansive phase. So, for example, if our universe had bounced one time, that is, it contracted and expanded, the CMB radiation in the new expansive phase would be 2 times greater than the starlight in that new cycle. If our universe had bounced 2 times, contracted, expanded, the CMB radiation in the new expansive phase would be 3 times greater than the starlight in that new cycle. And on and on and on, etc. So if the universe has been bouncing for an infinite amount of time, well then it would seem that the CMB radiation would be infinitely greater than our current starlight in our particular expansive phase. But point in fact, physicists tell us that the CMB radiation is not infinitely greater than our current starlight, but it's only 100 times greater. Therefore, the universe could not have been bouncing for an infinite amount of time. If it bounced at all, it could have only bounced 99 times. So in light of these 3 facts of entropy and the law of entropy, I think one can successfully argue against an eternal bouncing universe. And so in response to this eternal oscillating universe theory, I think one could quote Dr. Alexander von Lincoln in his book Many Worlds in One, where he writes, "Cosmologists must face the problem of a cosmic beginning."